with this entire architecture that you see, right? This entire architecture now today handles around 500 million tweets per day on an average. So that's a huge traffic to manage. Hey everyone, welcome back to the channel. So in today's video, we're going to see and explore how Twitter has achieved its massive scalability and stability of its search infrastructure, and we'll see how it is able to cater, approximately 500 million tweets a day. That's a huge number, right? So we'll focus on three key components. First one is the proxy service, then there is a ingestion service, then there is a backfilling service. All right. So these three services will explore and will then explain how Twitter gradually evolved their systems throughout the years, and they were able to handle this massive scale, right? So to start with, so initially when Twitter was in its beginning stage, Twitter search infrastructure allowed a direct interaction between the clients and the Elasticsearch cluster for querying, all right? So Elasticsearch is used for storing text-based data, and it's highly scalable, and its search infrastructure is quite impressive. Right? That's why they went for Elasticsearch. So while this simple interaction between client and the Elasticsearch cluster directly through a service, obviously there will be a client service in between. It's not directly the client wala thing. So we can think of it as a client service. Okay, to which the user is interacting with. All right. So user request will come to to a client service, and the client service will interact with the Elastic search cluster and then give back the result. So under normal condition, it worked fine, but the setup started to face significant challenges during high traffic periods, which led to potential bottlenecks and instability in this architecture. So to address these challenges, what they did, they went ahead with a proxy-based service. So what does this proxy service do? Now this is a proxy service in between, right? So this reverse proxy acts as an intermediary between the clients and the Elasticsearch clusters, which effectively separates the read and write traffic. Some of the benefits of this proxy servers were, there was a unified entry point, obviously. All the client requests are funneled through a single gateway here, which simplifies traffic management, right? It also enabled them to collect the metrics in an efficient and enhanced manner. For example, it gathers all the detailed data on request type, success rates, cluster health, and all those request related metrics. They were able to collect it effectively. And one of the main benefit, the final and main benefit that they got from this proxy service was flexible routing and throttling benefit. Now, what does that mean? By managing traffic flow using a proxy service, it prevents any single cluster from becoming overwhelmed, right? I mean, this is just one cluster. They might have a cluster, another cluster like this, right? They might have multiple clusters. They have multiple Elasticsearch clusters. So this proxy service prevents any particular single cluster becoming overwhelmed or overloaded, which indirectly improve the overall stability of the infrastructure. So they could add then rate limit, then throttling in a better and controlled manner. So they could easily add rate limiting basis on the user or IP address. So on an average, this proxy service was able to manage the bottlenecks that they faced in their earlier plain simple architecture here, and they could handle a stable scale with this architecture. In this architecture also, as the load gradually increased more and Twitter became more popular, it grew to millions of tweets per day on an average. I mean, it started to get millions of tweets a day. So this infrastructure now could not handle that load. So Twitter often used to experience sudden spikes in traffic due to, let's say, some trending topics or viral content, or some popular person tweets something about something, then suddenly it becomes a viral content, right? So those virality infrastructure was not able to handle effectively. So to handle this, what they did, they came up with the ingestion pipeline and backfilling services. Now I'll discuss about those things. So let me just change the slide. So this is the entire architecture that we are going to discuss right now. So with this architecture, they were able to handle around 500 millions of tweets a day. Now how did they do that? The first one is the ingestion service. Now the ingestion service was developed to mitigate the issues which the previous architecture experienced. What does it do now? This ingestion service basically queues the incoming request. Let's say incoming requests are coming, right? Let's say there is a read traffic and a write traffic. Write traffic means you want to create a new tweet. Read traffic means you want to browse the existing tweets. So the proxy services effectively split the read and write traffic, and the incoming data that is coming, write traffic, was queued in a dedicated Kafka topic. There was each Kafka topic for each Elasticsearch cluster. Similarly, if they have multiple clusters like this, they will have another Kafka topic per cluster basis. Right? Now, instead of writing the tweets directly to the Elasticsearch databases cluster, The tweet will go to the Kafka topic first. Based on the load in the Kafka topic, there will be multiple workers that will be batch processing the tweets present in the Kafka topic, and workers will then read from these topics and send a batch request to the clusters. They will write the tweets to the database, then they will index the tweets in the Elasticsearch. All those things were performed efficiently. So batch processing was the second key activity of this ingestion service. Now another benefit of this or usefulness of this ingestion service was to adaptive traffic management. Now what do you mean by adaptive traffic management? Now with this ingestion service, the service listens for back pressure signals. For example, somehow the Elasticsearch cluster is, let's say, overloaded, right? It is handling, it is experiencing a high CPU or RAM usage, so that is kind of a back pressure signal. So that signal will be sent to the ingestion service, and ingestion service will auto throttle for a period of time. It will reduce the pressure on the Elasticsearch by not sending the traffic to it, and then it will retry with the backup strategies to ensure that clusters are not overwhelmed or overloaded. So that's what the beauty of this ingestion service. It's basically worked in a async manner to manage the write traffic in an entire architecture. All right. So this approach effectively smooths out the traffic spikes that we see when there is something viral content is posted, right? People will start commenting on it, they'll retweet it, a lot of things, a lot of write traffic will come. So this ingestion service ensured consistent performance, and even during peak times it performed very smooth in a smooth manner. And obviously the read traffic will go directly to the Elasticsearch cluster, because the read traffic you cannot work in a async manner, right? It has to be on real time. So now we'll discuss about the backfilling service. What is the use of this backfilling service, and why do we need a backfilling service? So at Twitter, they frequently need backfillings. Backfilling of what? Now, backfilling refers to any large data operation that adds up to missing data. For example, in what cases they will get the missing data? Let's say you are just starting with an empty Elasticsearch. You are just starting a new Twitter deployment from scratch, or you are adding or updating a field in your schema, or data is missing in your entire cluster, let's say due to some downtime. I mean, Twitter was down for some time, sometimes, or some period of time, let's say, and during that period the writes were not performed effectively because the cluster was down. It was not able to write the traffic, write the tweeters to the Elasticsearch cluster. So in those cases, there will be possibility of getting a missing data. So these are some of the common reasons that Twitter needed a backfilling concept. All right. So in order to handle these cases, they came up with a backfilling service. A backfilling operation typically happens on the scale of sometimes thousands of terabytes or hundreds of terabytes, and sometimes millions and billions of terabytes too. In order to handle this backfilling data, I mean backfilling of the missing data, they used an old workflow where there was a custom scalding component, which is nothing but a Scala on Hadoop for big data operation. They had a custom sink which will create a HTTP client, which will then do the map reduce jobs, and then will try to write it to the Elasticsearch cluster. So these traditional backfilling methods opened multiple connections, which resulted in a degraded query performance or even cluster failures. So to address this, Twitter introduced these backfilling services. So these backfilling services contain three key components. The first one was the sink. So this is the sink. So sink acts as an entry point, right, to the partitioning and storing the data temporarily. So the sink takes in a stream of data, tweets. Data is in the tweets, to index and converts the data to indexing request. What is the indexing request? Let's say tweets are coming, right? So if tweets are coming, they have to be indexed in the Elasticsearch cluster. Without indexing, the read performance will drastically degrade. That's why you need indexing. Now, if I just show you a sample of indexing, you can see from here how it sample index looks like. If let's say these are the three tweets, right? Winter is coming, out is the furry, the choice is yours. Then they are indexed like this. I mean, based on this is just one sample how indexing works inherently in Elasticsearch cluster. So the bottom line is the incoming tweets have to be indexed to make the search faster. So I'll put a link to this blog in the description section. You can go through it and read it in detail. All right. So as the incoming data comes, the sync service, basically the sync component of the backfilling service, creates indexing request, and then partitions and then saves the data to a temporary service in a Hadoop partition HDFS format. So after this process, the sync then initiates a call to the orchestrator. So once the data indexing request, batch indexing request, terabytes, petabytes, millions of terabytes of data and thousands of terabytes of data is indexed and the index requests are created, They're stored in HDFS format in the Hadoop partitions. Then a request is created to the orchestrator. Then what is the job of the orchestrator? Now this orchestrator coordinates between the sink and the Elasticsearch clusters. So this is my Elasticsearch cluster, right? This is my Elasticsearch cluster. So this orchestrator will then coordinate between these two, and it will then launch dynamic number of workers to start the backfill. Then once the workers are triggered or workers are launched, these workers will then consume data from SDF Hadoop partitions. And these are workers are basically small distributed applications that read the index request from the storage, SDFS storage, and then index the data into the Elasticsearch cluster. Those indexing requests will be passed on to the Elasticsearch cluster so that the indexing is done on the backfilling data as well. In real time, whatever real time traffic is coming, that is to getting indexed properly. But for the backfilling data also you need indexing, and indexing is not a light operation on the database. That's why they also went ahead with this async manner of backfilling services. All right. So this structured approach ensures that large scale data operations are conducted safely and efficiently, minimizing the impact on live clusters, and which help them maintain the optimal performance of their cluster. And with this entire architecture that you see, right, this entire architecture now today handles around 500 million tweets per day on an average. So that's a huge traffic to manage, and this cluster is able to, this architecture and infrastructure is able to do so in a smooth manner. To summarize, by implementing these services, Twitter has significantly enhanced the stability and scalability of its search infrastructure. The proxy services manage and routes the traffic, read and write traffic effectively. The ingestion service handles real-time data searches gracefully, and the backfilling service ensures large-scale data operations are performed without compromising on the cluster integrity. So that's about the today's video. I hope you learned something new about Twitter's internals and how its search system works effectively. So if you got to learn something about it, please drop a like. Let's target for 50 likes in this video. And please subscribe to my channel. I'm targeting to reach 3,000 subscribers by the end of this month. So keep supporting. So if you have any questions around this, let's discuss in the comment section. So thank you for watching this video, and I'll see you in the next one. Thank you.